Will learning more about problem solving make you a better problem solver? Not necessarily, but it can't hurt. Before we get into the meat of the video, I have a spoiler alert. I am going to talk about a lot of classic problems used by psychologists to study problem solving. And before I spoil each problem, I am going to put the pause symbol up here like this. And I would encourage you, if you've never seen the problem before, to pause the video and actually try the problem or the puzzle for a few minutes before continuing the video. Even if you can't solve it, it's much more fun and interesting to hear about the solution after you have actually attempted it first. Okay, on with the video. The classic understanding of problem solving comes from Herbert Simon and Alfred Newell's formulation of what problem solving actually is. Let's look at this well-studied problem here, the Towers of Hanoi. In this problem, the goal is to move all of these discs from the rod they begin on to the rod on the other side, but there's some rules involved. You can only move one disc at a time, and you can't place a larger disc on top of a smaller disc. From this basic puzzle, we can see many aspects of Simon and Newell's perspective on problem solving. There is a starting problem state, or game state, if you want to think about this as a game. That's the state as I presented it to you. And a problem solver can perform various operations on the problem to move to a different problem state. If this is the starting state here, I have two moves. Now I can only move the disc on the top because I can only move one disc at a time and they're all stacked together right now. And I can move it to the second rod or the third rod. In either case, the problem is in a different state now. Let's say I choose this one. Now I can move the second smallest disc to the empty rod or move the smallest disc to either of the two open rods. So moving it back to the first rod, of course, takes me back to the starting state again. In addition to having a starting state and having operations that change the state of the problem, there is also a goal state. This is the state when the problem is solved. These basic ideas describe what is called a problem state space. The problem state space describes all the states of the problem and the operations that you have to move in between those different states. Here is the entire problem state space of the 3-disc version of the Towers of Hanoi. So the goal state is here, and the lines between the states indicate that you can move from one state to another in one move, or one operation. And so your effectiveness at solving this problem depends on how you navigate this state space. You're in one state, and how do you figure out how to get to the goal state? From this basic framework, a lot of interesting conclusions follow. In some cases, reaching the goal state is impossible. Doesn't matter what you do, you can't get there. Well, in that case, you have an unsolvable problem. And in some cases, the opposite thing happens. No matter what you do, you get to the goal state. Well, lucky us. In that case, you basically already have a solved problem. The difficulty of the problem is partly due to the complexity of this state space. I mean, we're going to talk about that more later too. How many states are there? How many paths are there to the goal state? How many possible operations are there at any given point? Now that determines the complexity of the decisions we make at any particular state. The state space idea applies to two-player games as well. Chess begins in this state and has a well-defined goal state where one of the kings is captured. And players alternate transforming the state of the game. And there's a lot of possible game states, which is what makes chess so difficult and so fun. The state space idea is also really critical for programming computers to solve problems. But a different puzzle can show us that things can get a little more complicated. This is the Chinese ring puzzle. It comes in different versions. Sometimes there are 5 rings, sometimes there are 7 rings, sometimes there are 9 rings, but the goal is to remove all of the rings from the metal bars that the rings are hooked to. But you can only remove certain rings at certain times, depending on the state of the other rings. Now, if you've never seen this problem before, it is really hard to solve. Most people just give up. But take a look at the state space for this problem. This is every state in the 5-ring version of the puzzle. Notice a couple of things. The state space is very small. There's only about a dozen states. The state space is also linear. You are either moving toward the solution or you are returning to a state that you were in before. If the state space is so simple, what makes this problem hard? The problem is that people don't understand what state they are in, and they don't understand how to move from state to state effectively. This makes the Chinese ring puzzle quite a bit different than chess or other strategy games. In chess, you always see where the pieces are, which defines the game state. And if you know how the pieces move, it's trivial to know whether you can get from one game state to another. For the ring puzzle, if you remove confusion about what state people are actually in, like if you use a computer simulation that makes the state more clear, then people solve this puzzle at much higher rates. So the Chinese ring puzzle illustrates another aspect of problem solving. Problem solving is not just about the nature of the problem. For any well-defined problem, there is a literal state space that comes about once you define the rules and the goal state. But as problem solvers, how we navigate that problem space depends on how we interpret that problem space. Another example will help us take this idea a little bit further. I have some cards with letters on one side and numbers on the other. Here are 4 of them. We're going to try to figure out whether every card with a vowel on it has an even number on the back. But we can only turn over 2 cards. Which 2 cards should we turn over to know whether or not we are violating this rule? This is a hard problem. Before I tell you what the answer is, I want to show you a different problem. Imagine that you are a police officer on duty. It is your job to ensure that people conform to certain rules. The cards in front of you have information about 4 people sitting at a table. On one side of a card is a person's age, and on the other side of the card is what the person is drinking. Here is a rule. If a person is drinking beer, then the person must be over 21 years of age. Select the card or cards that you definitely need to turn over to determine whether or not the people are violating this rule. The vowels and numbers example is known as the Wason 4-card selection task, and it's one of the most well-studied puzzles in all of psychology. There are hundreds of studies exploring how and why people choose the wrong cards. Most people will choose the vowel card and the even card, but the card with the even number on it tells you nothing about the truth of this statement. No one said that cards with consonants on them can't have even numbers on the back. The statement we are trying to evaluate says nothing about consonants, only that vowels must have even numbers on the back. The right card to pick is actually the 7, because if it does have a vowel on the back, then it violates the rule. Of course, if the A has an odd number on the back, it also violates the statement. People have an easier time with that one. Here's the thing. The drinking age example and the Wason card example are the same problem. They have the exact same state space. But people do pretty well on the drinking age problem and not very well on the Wason card problem. One explanation is that the real-world context of the drinking problem makes it easier to reason about it. You can easily imagine an underage drinker which violates a rule that a lot of people are familiar with. It's harder to imagine that a card with an odd number on it and a vowel on the back is an important violation of some rule that you were just told a few seconds before you did the task. So now we have 3 things that are affecting how we solve problems. There's the underlying nature of the state space itself and how complex that is. There is our interpretation of the problem, so figuring out what state we're in, figuring out how to move to a different state. And there is the context of the problem, which affects how we think about the problem. So that describes one branch of problem solving. But what about a problem like this one, the candle problem? Using the items on the table, attach a candle to a door so that it can burn properly. Among the available objects are a book of matches and a box of tacks. Almost everyone has heard of this one before, but if you haven't, take a moment to think about it and see what you would do, because I'm going to say the solution right now. The solution to this problem involves using the box of tacks as a shelf to hold up the candle. Usually people don't think of using the box of tacks because we have a kind of what's called like functional fixedness. When we look at the box, it's serving the function of a container. And it doesn't strike people that the box is itself a tool that we can use to solve the problem. This is not like chess. The main hurdle here is not searching different problem states. The candle problem is closer to the Chinese ring puzzle. The main hurdle is about representation. And once you re-represent that box of tacks as a tool that can help you solve the problem, usually the solution comes all at once. Psychologists usually call these kinds of problems insight problems. The experience of solving an insight problem is quite different than the experience of solving a non-insight problem. Those were the ones we were talking about earlier. Those are usually called incremental problems because you kind of have to build up the solution incrementally, or standard problems, or normal problems, or non-insight problems. People can't decide what to call these. At least that's the traditional argument. With an insight problem, the problem seems impossible when you are at an impasse and you are just banging your head against the wall, going over the same possibilities over and over and over again, and knowing that these possibilities don't work. And at some point, as you repeatedly go over the possibilities that you know don't work, you can come to a realization that all of a sudden solves the problem. Another interesting difference between incremental problems and insight problems is that with incremental problems, you can feel yourself getting closer to the solution. You know about how far you are from a solution. But with insight problems, you don't. There are at least two kinds of barriers that seem to prevent insight from happening. And to talk about those barriers, I want to talk about another kind of problem. These are Roman numeral matchstick problems. We can set up a math problem with Roman numerals, like this. Then we can ask ourselves, is this equation true? No, 3 plus 3 does not equal 4. Now the problem is, how do we move a single matchstick to make this equation true? Why don't you give it a shot first? Now for this problem, we can move this matchstick over to the right of the Roman numeral 5. So this makes the equation true because now it reads 3 plus 3 equals 6. In this problem, the IV stuck together forming the number 4 is a chunk. Something that we perceive to be whole, that is, we perceive it to be the number 4, but that can be also broken up into its component parts. It could also be broken up into 1 and 5. And then these parts can be recombined to create the number 6. Sometimes we have trouble moving between different levels of the chunk. Let me show you what I mean. Here's another problem to try. Right now it reads 11 equals 3 plus 3. Now remember, we can only move one matchstick. So we have to figure out which matchstick we can move to make the equation true. Solving this problem requires decomposing a harder chunk. Instead of pulling apart two numbers, you have to realize that the larger chunk that forms the X can be arranged into a V, making the equation true. So now it becomes 6 equals 3 plus 3. Let's try another problem. This one reads 9 equals 6 minus 3. Now take a moment to work on this problem. This problem is about a second barrier to insight, which are constraints. That's when our initial representation of the problem in our minds contains an implicit assumption. Now this assumption ends up constraining our search space so that we never get to search the right solutions to the problem. Now the previous examples all dealt with changing numbers and not the operators. To solve this problem, we have to let go of that constraint and move a matchstick from the equal side on the left to the subtraction side on the right. So that way we can get the true statement 9 minus 6 equals 3. This is the same kind of barrier to insight that we talked about with the candle and matchstick problem. Okay, this is the last example of these matchstick problems. Give it a shot. Now it reads 6 equals 6 plus 6. This requires us to relax another kind of constraint, that an equation can only have one equal sign. If we move the matchstick in the plus sign to make it read an equal sign, then the equation becomes true. 6 equals 6 equals 6. One thing to notice from these examples are that certain chunks and certain constraints are easier than others. So for instance, most people find these two problems to be easier than these two problems. Another thing to notice is that you can create biased problem representations through problem solving. If you solve a series of problems successfully with the same approach, your ability to see a different approach when you come to a new problem will be impaired. This is what psychologists call mental set. Before you started solving any problems at all, the chance that you might come up with this strategy or that strategy might be roughly the same. But as you solve more and more problems successfully with strategy A, your brain gives you preferential access to that strategy. It's kind of like saying, pick me, pick me, pick me. That might have been what happened when I gave you two problems in a row that ask you to manipulate the Roman numerals and not the operators. So that when you got to that third problem, it was probably a little bit harder to see that you could manipulate the operators as well, compared to if you had never seen those first two original problems and I just asked you the third problem in the very beginning. In these cases, it seems to be that only when the existing strategy continues not to work and not to work and not to work, that you reach an impasse and finally your mind kind of expands to include other potential strategies or solutions. Even though psychologists have traditionally discussed incremental and insight problems as being two fundamentally different kinds of problems, whether someone has the insight experience depends on more than just the nature of the problem. People will report having insight experiences in what would traditionally be called an incremental problem. People report having no insight experiences, but solving the problem successfully, even in the context of what would traditionally be called an insight problem. A lot of problems in math and science incorporate both incremental or analytic kinds of elements and insight or conceptual kinds of elements together. Paul Zeitz, who is a renowned mathematics teacher, talks about math problems involving a crux move, or sometimes several crux moves. Now, what he's talking about is really the insights needed to solve the problem. But just because you got the crux move, that doesn't eliminate the need for doing all of the other hard work to find the solution. In my opinion, it's best to think of incremental and insight problems as almost pure forms that psychologists try to distill when they are studying these cognitive processes, but that most problems, most realistic problems, are going to have elements of both. Speaking of realistic problems, what do all of the fun little puzzles that we've looked at so far have to do with actually solving problems in the real world? For almost as long as psychologists have been studying problem solving, they have made a distinction between well-structured problems and ill-structured problems. Now, well-structured problems are exactly the kinds of problems that we have been looking at earlier. Even the insight problems that we were talking about have well-defined goal states and a fixed set of operations, and therefore a well-defined state space whether the problem solver realizes it or not. But most of the hard, realistic problems that we confront in life are not like that. What about the problem of providing cheap, reliable, safe, and clean public transportation systems? What about the problem of addressing climate change? What about the problem of sending humans to Mars? For each of these, the goal states are not defined precisely. Now, there are also many elements at work interacting in complex ways, and those elements themselves aren't necessarily well-defined. Problems like these are considered ill-structured problems as opposed to the well-structured ones that we have been talking about so far. Now, the lessons from well-structured problems do not necessarily go away when we start to meet the real world. In any kind of problem, we still have to figure out what the alternatives are, evaluate those alternatives, and pick one. And even with ill-structured problems, we are still moving through a search space, even if it's poorly defined. But two themes loom a bit larger when we're talking about ill-structured problems. The first has to do with problem representation. Understanding the nature of the problem takes on a much larger role in ill-structured problems. Remember that with the insight experience, once we find the right representation, the solution is super obvious. With ill-structured problems, it's not immediately obvious if a given representation of the problem, if a given understanding of the problem is going to be ultimately that helpful. It might seem helpful now and might lead us astray later, or it might seem kind of stupid now, but maybe it is the right thing after all, and we can gain a lot of insight from it. It's precisely because things are not obvious in ill-structured problems that another element comes to the fore: arguments. What is the proper way to understand the problem? What is the proper way to represent the problem? All representations simplify things, but which representations or which combinations of representations simplify things correctly? We can argue about it. With ill-structured problems, there's not one shining goal state that everyone understands and agrees upon. Rather, there's outcomes that we'd like to have, and often the solutions involve trade-offs in those outcomes. So which outcomes do we prioritize? Well, we can argue about it. In a lot of cases, the real-world problems don't end. New events come along to wreck the perfectly good solutions that we had. Our standards change, so what was once considered to be a good solution is no longer considered to be a good solution. Short-term solutions that seem good can create deeper, long-term problems. So arguments are going to come up again about how to solve these problems. Personally, I view well-structured problems as interesting models that can help illustrate the dynamics that are going on when we solve problems. It's good to keep in mind that there is a trade-off when we simplify these problems down to try to isolate some kind of key component of problem solving, because we've sacrificed some things. We've made it less realistic. We've made it less dynamic. We've made it less contextual. But how does someone actually become a better problem solver? Well, to answer that question, I want to look at yet another kind of problem. So we have a bunch of toothpicks and they are arranged like so, and we want to take away 5 toothpicks and leave 3 squares. How do we do that? If you've never seen this kind of problem before, you might start out by just trying new things out. So you take away some toothpicks and you see what happens. If you take away these 5, you're left with 4 squares, which is not quite what we want. We want 3 squares. You can also take away just 4 toothpicks and get 3 squares, like 2 small ones and 1 big one, but that's not exactly what we want either. What we're doing at this stage of the process is employing what's called a domain general strategy. And the most general strategy that there is to try stuff out and see what happens. Now, researchers have a very particular word for this kind of thing, which is called trial and error. You may have noticed that my first 2 attempts here were guided by the prompt of the problem. So I tried to take away 5 toothpicks that seemed like sensible choices, but I didn't get the right solution. And in the second attempt, I tried to think, well, what could I do to create 3 squares without paying as much attention to the fact that I need to remove 5 toothpicks and not 4 toothpicks. So since I didn't find an immediate answer, I can try to be more systematic. Let's remove toothpicks one at a time and see what happens. So I can remove 1 toothpick from the corner and another toothpick from the corner, and that leaves me with 5 squares. Removing a toothpick in the middle kind of leaves me with a rectangle that I don't know what to do with. That doesn't seem particularly helpful right now. What about the edge pieces, which are only found on the top and the bottom here? Now there are only 2 edges, but notice if I remove one of them, I essentially remove a whole square. So if you're keeping track now, we've got corner pieces, we've got center pieces, and we've got edge pieces. And each kind of piece does something a little bit different. I have to remove 2 corner pieces to remove a square. I can remove 1 edge piece to remove a square. And I kind of have to remove, I guess, 4 center pieces to remove 3 squares, turning a 4 square box into a 1 square big box. Now, if I think about this knowledge that I have now about how the edges and the corners and centers work, I can probably come up with a solution to this problem more easily. If I'm starting with 6 boxes and I need to get to 3 boxes and I have to remove 5 toothpicks, well, removing 2 toothpicks from a corner removes 1 box, 2 toothpicks from another corner removes another box, and 1 toothpick from an edge removes another box. So that's 3 boxes, 5 toothpicks. If you look at the problem, you can either solve it in this way or in this way. The important part here is not that I have solved the problem. Notice what's happened here. As we've been searching for a solution, we've gained knowledge about the nature of these problems. This is what's called domain-specific knowledge, and it's what lets me solve the next problem a little bit different than the way that we solved the first problem. If we face a much bigger problem, I still know that I can take 2 toothpicks away from a corner to take away a square, 1 toothpick away from an edge to take away a square, and I can do something funky in the center to get big squares if I want. And as we start to see more shape problems like these, we'll start to notice more of these kinds of patterns, which helps us to solve these problems more and more efficiently in the future. Now, you might think that once we find a more efficient way of solving a certain kind of problem, we will just keep using that efficient way over and over again. We work for a little while, we find a new strategy, we start using that new strategy, then we find an even better strategy, and then we use that even better strategy, and it just works like that. Strategic change, however, is a little bit more subtle than that. We might start off with inefficient strategies and eventually use more efficient strategies, but as we develop our knowledge and understanding, what tends to happen is we use a mixture of strategies together as we're testing out which strategies can be used in which situations and which things are really more efficient and kind of still in a habit of using, say, an older inefficient strategy. Research on children and adults all suggests that we don't just abandon old strategies just because we found something new. We kind of gradually change the mix of strategies that we use to solve problems. Regardless, in the big picture, we have moved away from using domain general strategies and towards using domain-specific strategies. Now let's take what we've learned from these toothpick problems and apply it to a different set of problems. The problem of designing RNA molecules. Like DNA, RNA has 4 different kinds of bases, and they form special base pairs. And the sequence of bases that you have will determine the kind of structure that the RNA molecule folds into. So we want to get it to fold like this. Now, how can we use what we learned from the toothpick problems on this kind of problem? You might see that there's a problem here. What we learned from the toothpick problems doesn't really help us understand what we need to do for the RNA problems. At least it's not immediately obvious how these shape problems could help us in this RNA domain. There are a lot of different problems in the world, and understanding one area really well doesn't particularly help us to understand another area very well. When somebody says something like, I want to get better at problem solving, they usually have a problem domain in mind. So they're thinking about mathematical problems or physics problems or medical diagnostic problems, something. Generally speaking, when we get good at problem solving, we get good at solving a particular class of problems, a set of problems that share certain features with each other. That way we can leverage our domain-specific expertise to perform really well. All chess problems share the same constraints. They're all on an 8x8 board. All the pieces move in the same way. The goals of the problem come in a limited number of forms. There's a set of strategic concepts that can be applied to a wide variety of chess situations. If we had to rely on domain general techniques like trial and error all the time, we just wouldn't get very far. Part of the goal of these domain general techniques is to help us understand the domain more effectively. So it's knowledge of the specific features of the domain that drives high levels of performance. If problem-solving domains all require different skills and knowledge to perform well in, is there really nothing we can learn from solving one kind of problem that we can apply to another kind of problem? This question strikes at something that is absolutely at the heart of learning, and that is transfer. Transfer is the idea that we can take something that we learned in one situation and apply that to a different situation. I'm going to talk about 3 different kinds of things that I think do transfer between problem domains. First, certain large ideas cross problem domains. There's something similar between these shape problems that I was talking about earlier and the game of Go, or StarCraft, or military strategy more generally. The terrain matters. Centers and edges and corners often behave differently from one another. So it's not the domain-specific idea that I can remove 2 toothpicks and then I also get to remove a square, like in the shape problems. It's a more general, abstract idea. The idea that terrain matters isn't a substitute for domain-specific knowledge, but it can help us generate domain-specific knowledge more efficiently. If we tackled those shape problems from the beginning and looked at them and thinking, okay, the terrain matters, so something about the edges and the corners and the centers are probably different. Well, that idea could help guide us to learn what the domain-specific knowledge is more quickly than if we just apply trial and error at the beginning. Of course, even though a general idea like terrain matters comes up in all kinds of different contexts, there are still lots of problems where it just doesn't matter whatsoever, like in algebra problems. Other ideas which cross many different domains are things like parity, which is the idea that every item can either be on or off, and often you can solve a problem more quickly by looking at the problem that way. Or symmetry. There's some pattern in one area that reflects a similar pattern. None of these apply to every single problem in the universe. It's just that they come up in surprising ways. So there are certain ideas that cross domains. There are also certain strategic problem-solving behaviors that seem to cross domains. Organizing what you know is almost never a bad thing to do. Explicitly stating your assumptions is almost always a good thing to do. Estimating the cost of testing various kinds of solutions and then eliminating the easy to test or the obvious solutions is often a very good thing to do. All of these are examples of certain problem-solving approaches that just seem pretty useful across many different kinds of domains. And there are plenty more of these basic ideas. Of course, how you should be organizing what you know depends on the domain. And what your assumptions are depends on the domain. And how easily it is to rethink or reframe the problem depends on your knowledge of the domain. So just telling people you should really organize what you know, or you should really state your assumptions more explicitly, is not really helpful. It's more like you need to get experience using different kinds of representational tools to organize what you know in different kinds of domains to have a decent shot of using those same tools to help organize a new domain. Finally, it seems like there are certain personality traits or learned behaviors that either help develop problem-solving expertise, or maybe develop with problem-solving expertise, that you see happening across domains. The tendency to stop and think about what you're doing instead of just leaping to the most intuitive first answer that comes to mind is one of those. There's lots of studies just focused on this one trait. Perseverance is another one. In most domains, it helps to just keep going. The tendency or ability to find ways to check intermediate and final solutions to make sure that you're not screwing up somewhere. These are all personality traits and abilities that either prevent you from tricking yourself or otherwise help you to find really good solutions. In a sense, the problem of getting better at problem solving is really the problem of getting better at learning. What I mean by that is that to solve hard problems requires that you learn as you are solving the problem. If you don't have to learn anything while you're solving the problem, then what you're doing is just kind of performing an exercise. It's not really fundamentally a problem for you because you already know how to do it. Bringing the tools with you, the conceptual tools, the strategic tools, the attitude, and being prepared to learn from the problem as you are solving it is ultimately, I think, what distinguishes good problem solvers who can solve problems in lots of different domains from problem solvers who can't. So there is so much more to say about problem solving, but I am going to stop the video here because I intended on making this video like 5 months ago and I still haven't made it. So let me know if you have questions or comments or thoughts in the comment section below. I'll try to read them occasionally and get back to people, and hopefully we have some good conversations. Thank you for watching. You can see some of my other videos about problem solving in this playlist here. And this is the last time you will see this background because I am moving in a couple of days back to the States. So I will see you there. Okay, bye.